Article 210.19 covers branch circuits and conductor sizing. The ampacity of a conductor must not exceed the rating of the branch circuit. For example, a 20 amp branch circuit typically requires number 12 American wire gauge or AUG conductors, assuming standard insulation types and installation methods as per the National Electrical Code or NEC. However, the conductor size may need to be increased to address voltage drop. Voltage drop on a branch circuit should ideally not exceed 3% for feeders and 5% for branch circuits to ensure efficient operation of equipment. Now consider a 200-foot branch circuit. Due to voltage drop, number 10 AWG conductors might be considered. Calculating the voltage drop for this specific scenario is essential. A 200-foot branch circuit using number 10 AWG conductors may exhibit a voltage drop of approximately 7.5%, which exceeds the recommended 5% limit. Therefore, using number 10 AWG conductors for the entire 200-foot run may not be compliant or efficient. Let's discuss tapping. A tap conductor, such as number 12 AWG, can be used, but it must adhere to specific requirements. The tap conductor should not exceed 80% of the ampacity of the branch circuit conductor, which in this case is the number 10 AWG. For a 20 amp branch circuit, 80% of the ampacity would be 16 amps. Number 12 AWG conductors are generally rated for 20 amps. In this scenario, they may be acceptable for the tap, provided the load does not exceed 16 amps. In summary, using number 10 AWG conductors for a 20 amp branch circuit that is 200 feet long may not be permitted due to excessive voltage drop. Tapping with number 12 AWG conductors is permissible, but the tap must not exceed 80% of the branch circuit's ampacity, which equates to 16 amps in this case. Always consult local electrical codes and regulations, as interpretations may vary. The National Electrical Code, or NEC, provides guidelines for electrical installations to ensure safety and proper functioning. When determining conductor sizes, factors such as ampacity, voltage drop, and ambient temperature must be considered. Ampacity refers to the current carrying capacity of a conductor. The NEC provides tables that list the ampacity of various conductor sizes based on their insulation type and operating temperature. Voltage drop is the reduction in voltage that occurs along a conductor due to its resistance. Excessive voltage drop can cause equipment to operate inefficiently or not at all. The NEC recommends limiting voltage drop to 3% for feeders and 5% for branch circuits. Ambient temperature is the temperature of the surrounding environment. High ambient temperatures can reduce the ampacity of conductors. The NEC provides correction factors that must be applied to the ampacity of conductors when they are installed in high ambient temperatures. When tapping a conductor, it is important to ensure that the tap conductor is properly sized and protected. The tap conductor must have an ampacity that is at least equal to the load that it will serve. The tap conductor must also be protected by an overcurrent device, such as a fuse or circuit breaker. The overcurrent device must be sized to protect the tap conductor from overload. When making electrical connections, it is important to use proper techniques and materials. Connections must be tight and secure to prevent overheating and arcing. Electrical connections should be made in approved junction boxes or enclosures. Always follow the manufacturer's instructions when installing electrical equipment and components. If you are unsure about any aspect of electrical work, consult a qualified electrician. Electrical work can be dangerous, and it is important to take precautions to avoid injury. Always turn off the power before working on electrical circuits. Use insulated tools and equipment. Wear appropriate personal protective equipment, such as safety glasses and gloves. Never work on electrical circuits in wet conditions. By following these guidelines, you can help to ensure the safety and reliability of your electrical system. Remember to always consult the latest edition of the National Electrical Code and local regulations for specific requirements in your area. Staying informed and compliant is crucial for safe and effective electrical installations. Additional factors to consider when designing branch circuits include the type of load being served, the distance from the power source, and the presence of any other electrical equipment in the vicinity. Different types of loads, such as lighting, motors, and appliances, have different current requirements and operating characteristics. It is important to select conductors and overcurrent protection devices that are appropriate for the specific load being served. The distance from the power source can affect the voltage drop in the circuit. Longer circuits will experience greater voltage drop than shorter circuits. It may be necessary to increase the conductor size to compensate for voltage drop in long circuits. The presence of other electrical equipment in the vicinity can also affect the design of the branch circuit. Electrical equipment can generate heat, which can affect the ampacity of conductors. It may be necessary to direct the ampacity of conductors that are installed near heat-generating equipment. When designing branch circuits, it is important to consider all of these factors to ensure that the circuit is safe, reliable, and efficient. The National Electrical Code provides detailed guidelines for designing branch circuits. It is important to consult the NEC and local regulations for specific requirements in your area. In addition to the factors already mentioned, it is also important to consider the type of wiring method being used. Different wiring methods have different ampacity ratings and installation requirements. Some common wiring methods include non-metallic sheathed cable, armored cable, and conduit. Non-metallic sheathed cable is a type of cable that is commonly used in residential wiring. It consists of 2 or more insulated conductors enclosed in a non-metallic sheath. Non-metallic sheathed cable is relatively inexpensive and easy to install. Armored cable is a type of cable that is used in commercial and industrial wiring. It consists of 2 or more insulated conductors enclosed in a metal armor. Armored cable is more expensive than non-metallic sheathed cable, but it is more resistant to damage. Conduit is a type of raceway that is used to protect electrical conductors. Conduit can be made of metal or plastic. Conduit is typically used in commercial and industrial wiring, but it can also be used in residential wiring. When selecting a wiring method, it is important to consider the type of environment in which the wiring will be installed. Non-metallic sheathed cable is not suitable for use in wet or corrosive environments. Armored cable is more resistant to damage than non-metallic sheathed cable, but it is more expensive. Conduit provides the best protection for electrical conductors, but it is the most expensive wiring method. When installing electrical wiring, it is important to follow all applicable codes and regulations. Improperly installed wiring can be a fire hazard. It is also important to use the correct tools and equipment. Working with electricity can be dangerous. If you are not comfortable working with electricity, it is best to hire a qualified electrician. Other considerations include the derating factors for conductors in conduit. When multiple conductors are installed in the same conduit, the ampacity of each conductor must be derated. The NEC provides tables that list the derating factors for different numbers of conductors in conduit. It is also important to consider the grounding requirements for electrical systems. Grounding is the process of connecting electrical equipment to the earth. Grounding helps to protect people from electric shock. The NEC provides detailed guidelines for grounding electrical systems. Surge protection is another important consideration. Surge protectors help to protect electrical equipment from damage caused by voltage surges. Voltage surges can be caused by lightning strikes, power outages, and other events. Surge protectors are typically installed at the service entrance of a building. Arc fault circuit interrupters, or RFCs, are another important safety device. RFCs are designed to detect arc faults, which are a type of electrical fault that can cause fires. RFCs are typically installed in bedrooms and other areas where people sleep. Ground fault circuit interrupters, or GFCIs, are another important safety device. GFCIs are designed to detect ground faults, which are a type of electrical fault that can cause electric shock. GFCIs are typically installed in bathrooms, kitchens, and other wet locations. By following these guidelines, you can help to ensure the safety and reliability of your electrical system. Remember to always consult the latest edition of the National Electrical Code and local regulations for specific requirements in your area. Staying informed and compliant is crucial for safe and effective electrical installations. Let's also delve into the practical implications of these code requirements. Imagine you're setting up a workshop in your garage and need to run power to a new set of outlets for your tools. The distance from your main electrical panel to the garage is 200 feet. You're planning to use a 20 amp circuit. If you initially consider using number 12 AWG wire, which is commonly used for 20 amp circuits, you might encounter voltage drop issues over that distance. This means your tools might not receive the full 120 volts they need to operate efficiently, leading to performance problems or even damage to your equipment. By upgrading to number 10 AWG wire, you reduce the resistance and therefore the voltage drop. However, as we've discussed, even number 10 AWG might not be sufficient to keep the voltage drop within the acceptable 5% limit over 200 feet. In this case, you have a couple of options. Firstly, you could consider using a larger gauge wire, such as number 8 AWG, to further reduce voltage drop, or secondly, you could split the circuit into two shorter runs, each with its own 20 amp breaker. This would reduce the distance and, consequently, the voltage drop on each circuit. Now, let's say you decide to tap into the number 10 AWG wire at a junction box in your garage to run a shorter length of wire to a single outlet. You want to use number 12 AWG wire for this tap. According to the NEC, this is permissible as long as the load on the tap doesn't exceed 16 amps, which is 80% of the 20 amp circuit rating. This means you can safely plug in a tool that draws up to 16 amps into that outlet without overloading the circuit. It's crucial to accurately calculate the load you'll be placing on the circuit to ensure you stay within the limits. This involves adding up the amperage of all the devices you plan to use simultaneously on that circuit. If the total exceeds 16 amps, you'll need to either reduce the load or run a separate circuit. These examples highlight the importance of understanding and applying the NEC guidelines when designing and installing electrical circuits. It's not just about choosing the right wire gauge, it's about considering all the factors that can affect the safety and performance of your electrical system. Always consult with a qualified electrician if you're unsure about any aspect of electrical work. They can help you ensure that your electrical system is safe, reliable, and code compliant. Let's consider the scenario of running a 20 amp circuit to an outdoor shed located 200 feet away from the main panel. Due to the distance, voltage drop becomes a significant concern. Using number 12 AWG wire, which is commonly used for 20 amp circuits, would likely result in a voltage drop exceeding the recommended 5%. This can lead to dimming lights, reduced motor performance, and potential damage to sensitive electronic equipment. To mitigate voltage drop, upgrading to number 10 AWG wire is a common solution. However, even with number 10 AWG, the voltage drop might still be borderline acceptable, depending on the load. In such cases, consider using number 8 AWG wire, which offers lower resistance and further reduces voltage drop. Now, let's say you want to install multiple outlets in the shed and plan to tap into the main circuit run using number 12 AWG wire. According to the NEC, the tap conductors must be protected by an overcurrent device sized appropriately for the tap conductors. In this case, number 12 AWG wire is typically rated for 20 amps, but the tap rule limits the load to 80% of the main circuit's ampacity, which is 16 amps. This means you can connect multiple outlets to the tap, but the total load on those outlets must not exceed 16 amps. To ensure compliance, it's crucial to calculate the total load of all devices that will be plugged into those outlets simultaneously. If the load exceeds 16 amps, you'll need to either reduce the number of devices or run a separate circuit. Furthermore, consider the environmental conditions in the shed. If the shed is exposed to high temperatures, the ampacity of the conductors might need to be deaerated. The NEC provides tables that specify deaerating factors for different temperature conditions. It's also important to use appropriate wiring methods for outdoor applications. Underground wiring requires specific types of cables and conduits that are rated for direct burial. Above-ground wiring must be protected from physical damage and sunlight exposure. Grounding is another critical aspect of electrical safety in the shed. The shed must be properly grounded to prevent electric shock hazards. This typically involves installing a grounding electrode, such as a ground rod, and connecting it to the electrical system. Finally, consider installing surge protection devices to protect sensitive electronic equipment from voltage spikes caused by lightning or power surges. Surge protectors can be installed at the main panel or at individual outlets. By carefully considering all these factors, you can ensure a safe and reliable electrical installation in your outdoor shed. Always consult with a qualified electrician to ensure compliance with local codes and regulations. They can provide expert guidance and perform the installation safely and efficiently. Let's also talk about electrical safety in general. Electrical work can be dangerous, and it's essential to take precautions to prevent accidents. Firstly, always turn off the power before working on any electrical circuit. Use a voltage tester to verify that the circuit is energized. Secondly, use insulated tools and equipment to protect yourself from electric shock. Wear rubber gloves and safety glasses when working with electricity. Thirdly, never work on electrical circuits in wet conditions. Water is a conductor of electricity, and it can increase the risk of electric shock. Fourthly, be aware of your surroundings and avoid touching any metal objects while working with electricity. Metal objects can conduct electricity and cause electric shock. Fifthly, if you're not comfortable working with electricity, hire a qualified electrician. They have the knowledge and experience to perform electrical work safely and efficiently. In addition to these general safety precautions, there are also specific safety requirements for different types of electrical work. For example, when working on overhead power lines, it's essential to maintain a safe distance from the lines to avoid electric shock. When working in confined spaces, it's important to ensure adequate ventilation to prevent the buildup of hazardous gases. When working with high voltage equipment, it's essential to use specialized safety equipment and follow strict safety procedures. Always consult with a qualified electrician or safety professional to learn about the specific safety requirements for the type of electrical work you're performing. By following these safety precautions, you can help to prevent electrical accidents and ensure your safety. Remember, electricity is a powerful force, and it must be treated with respect.